My name is George. In this lesson, we will discuss hash tables, concepts, techniques, challenges, and a resolution of these challenges. A hash table is a data structure designed for very fast data retrieval. The core idea is simple. We take a key, apply a hash function, convert the key to an index in an array. For example, if we use the key 21, apply hash function modulus 10, we get index 1. That one will be position of the value 21 key in the array. The value is then stored at that location in the table. Hash tables are popular because operations such as search, delete, and retrieve are very fast on average. Because of this efficiency, hash tables are widely used in software systems, in databases, caching systems, and dictionaries. However, hash tables introduce an important challenge called collisions. A collision occurs when two different key maps to the same position in the array. In this example, we have the key 21 and the key 31. We apply the function mod10 to each. It returns 1, the position of both keys in the array. That is a collision of index of two values. Since both values want to occupy the same location in the array, the system must decide how to handle this conflict. Collisions are unavoidable because the number of possible keys is often larger than the number of possible indexes. The goal here is not to eliminate collisions entirely, but to handle them efficiently while maintaining fast performance. There are several strategies that could be used to handle collisions. We will discuss two of them, the chaining and the linear probing. With chaining, multiple values are stored at the same index in the array using a linked list or a chain. For example, value 21, 31, and 41 using the same hashing function modulus 10 return index 1. However, the keys can coexist in the same bucket using a linked list. The chaining is flexible and relatively simple to implement. On the other hand, we have the linear probing. Instead of storing multiple values in the same location, the system searches for the next available spot. For instance, if 21 occupies index 1, then the system searches for any available next position to store 31. Linear probing is simple and cache-friendly, but can reduce efficiency when we have large data cluster. Although the techniques are different, both aim to preserve fast lookup. These concepts are not just theoretical. They are widely used in modern computing systems and databases. For example, let's take AWS DynamoDB. DynamoDB is a service that stores NoSQL database. This service scales and expands horizontally every time we add more data, and the data is stored onto partitions. Every partition has its own unique partition key. Now, the partition key is hashed to determine where a data item is going to be stored. So the hash partition key provides the location. Then we could use secondary key, it's called also sort key, to retrieve the item data very fast. At high level, it is the same concept, a key transformed into a storage location. This demonstrates how foundational data structure like hash tables support real-world high-performance systems. I will now briefly explain the thought process behind designing this lesson in this way. In designing this short lesson, I intentionally used a concept-first approach. Bring the big picture in, highlight the concept, because hash tables can initially feel abstract to students, not easy to understand. So I started with the core idea, then introduced the problem, and then provided key solution to the problem and backed it up by real-world application. This type of structure helps scaffold learning gradually and reduces cognitive overload. I also intentionally limited the lesson to 2 collision resolution to keep the content focused within the time frame. Finally, as mentioned, I connected the topic to real-world application using AWS DynamoDB as an example. Beyond this content design and structure, student engagement is also very important and a key part in my teaching approach. I always try to engage the students through visual learning, interaction, and small practical examples. For instance, I might use a diagram and step-by-step visual to make abstract concepts easier to understand. I also use interactive questions throughout the lesson. For instance, I might ask the students what happens if 2 keys occupy the same index in the array. This will encourage prediction, prompt a discussion, active participation, and more questions from the students. I also prefer using small numerical key examples rather than major examples before we move into more advanced analysis. Finally, connecting such theory to real-world examples like DynamoDB help the students understand why these concepts matter beyond the classroom. Overall, my goal is to balance technical accuracy with accessibility and engagement. I hope you found this lesson useful and instructive. Thank you.